Good morning, guys. In this video, we're going to be going ahead and explaining how we get diffusion equations for vapors and liquids and comparing their dominant forces to see how we would calculate these in a realistic setting. So, gonna merge that down. So, for this first equation, what we're going to do is I'm going to show that for vapors in this case, diffusions are mostly dominated by kinetic forces in this case. So, if I were to create the diffusion equation here, uh, I'm going to use the textbook equation that we used in class to kind of show just the general behavior of diffusions for vapors in this case. I'll put vapor here just to kind of keep track and kind of talk about the variables as I write them along. So key thing with diffusion is that if ever there's temperature increasing, diffusion is going to go up. Particles get more excited, obviously, which increases their energy. And this is the power of 3 over 2. Now let's go ahead and get to the denominator here. I'll get to the coefficient in a second. It's a weird conversion with Avogadro and Boltzmann's constant. I'll get to that in a second. So let's go ahead and talk about this is the molecular diameter squared for A and B. Pretty straightforward. The larger the molecule is of radius is, the lower your diffusion is going to be. Think of it as just kind of bulkier particles moving throughout. Then we have a collision integral in this case, which usually this value is just derived by a textbook. You'll see something like T star, which all this is comparing is the thermal energy and the energy of intermolecular forces between A and B in this case. So usually in a textbook for a given mixture, you can find that value of the molecular collision, and then density, which is pretty obvious. The more dense the material is, the less diffusion you have in your system. And then this is multiplied. I'm just going to show the expanded form. The textbook had it in the compressed form. I'm going to do this expanded. This is the molecular weight of A plus 1 over molecular weight of B, kind of getting the same premise of things that get more bulky. As your weight increases throughout, this number gets smaller and smaller and smaller, which if this is being multiplied, means your diffusion goes down in general. So the Boltzmann constant and Avogadro's number, when you simplify all the units and get the final coefficient, it's something like 0.00266. And you can kind of, I was kind of talking through this as I was putting in every variable, but you can kind of see the general trends for how the diffusion for vapor works and see that it is very dominant by, it's very predominated by kinetic forces in this case, right? So liquids are a little bit different. If we look at the diffusion comparing something like A and B of liquids in this case, you have one equation for this. At least we did in the textbook. This is the Boltzmann constant multiplied by temperature over 6 pi, the atomic radius, and the viscosity of your system. So this is a fine theoretical equation. This is what we call the Stokes-Einstein equation. So this equation is good. However, it only allows us to express the diffusion for what is it? Infinitely dilute diffusion equations. So it's not a realistic context because it doesn't consider composition in this case. So we're gonna instead take the Vignes formula and we're gonna convert that so it considers composition of both A and B, right? Uh, let's see here. Diffusion of A and B should equal something like diffusion of A and B, and this is going to be the infinite one that we talked about. We can actually put infinite there for now. And then this would be in regards to B, though I'm just going to put this in molar fraction 2. This is liquid molar fraction 2. That's what X is in this case. And then this is multiplied by the infinite diffusion or infinite dilute diffusion of B and A multiplied by the molar fraction of 1. So you can also see uh, this one is impacted a lot more by the viscosity of the system. If I were to make an analogy to compare diffusions of A and B of if both in the vapor state and the liquid state, I would say look at something like water. If you look at something like water, the diffusion of vapor is very kinetic focused. That's why in low pressure situations where we're pretty close to the boiling point, ideal gas law works, right? Because we're assuming that there's very little to none intermolecular forces happening with each other, and that it's purely kinetic, right? But as we increase pressure, we of course have to include intermolecular forces, but mostly it's dominated by kinetic forces. This is juxtaposed to liquid forces. Think of surface tension. Liquid, unless there's an external force onto it, kind of wants to stick to each other. There's intermolecular forces such as hydrogen bonding that take place. And so it wants to kind of stick with each other, bunch together. So that's kind of the comparison between the diffusions of both vapor and liquid. I will pause for a second. I made a very pretty diagram for part two, so I'm going to go ahead and drag and show that really quick. All right. So this is my pretty diagram that I had made. My handwriting's really bad, so I wanted to just kind of pause and bring it back. So in this case, we're going to derive a equation of continuity for a unidirectional system, considering rate of formation. So that sounds like a lot of jargon, but I'll kind of talk through slowly, explaining what this problem actually is. So I said we have a unidirectional system, and I'm going to take molar flux coming in from the direction of d of z in this case. And I'm going to show how we can kind of derive an expression explaining how molar flux, concentration, and the rate of formation all kind of interact with each other in a system like this. So let's first define, I'm going to define what rate of formation is. So I'm going to say that R of 8 is and my iPad is fussy right now. Sorry about this. There we go. Sorry. So rate of formation in this case is just this is a per volume basis, meaning that for this system, we're considering all changes of d of z, d of x, and d of y for our entire system here. So if I were to write this down, this would be R of A multiplied by d of z, d of y, and d of x, not d of z. So that's kind of a rate of formation equation here. Now we have to consider the molar flux. So we've done a lot of problems like this right now. This is very analogous with a lot of homework one and homework two. We have molar flux entering a system in the cross-sectional area of d of x and d of y, and we have this molar flux plus the distance of d of z leaving the cross-sectional area. So to draw that, I'm going to make this the molar flux of the cross-sectional area of d of y and d of x. And then we're going to go ahead and subtract this by the molar flux of d of y, d of x, actually, sorry, d of a plus d of z, d of y, and d of x. And now we're going to set this equal to, notice I left this concentration in here. So what we want to observe is the change of concentration per volume basis with regards to some change of temperature. So this is going to be change of concentration multiplied by d of z, d of y, and d of x. And this is going to be over some change of temperature. So you can see we have a lot of like terms here. Every equation have d of y and d of x in this case, so I'm just going to do the lazy thing and just get rid of d of y and d of x. What that leaves us with is rate of formation and change of z direction. Then we have uh, Na minus molar flux of A plus d of z. And then we have the set equal to change of concentration multiplied by change of z direction and change of temperature. So this is going to be a very neat calculus moment. We have d of z over here. If we observe this equation over here, I'm going to kind of go ahead and single this out. What I'm going to do is divide every equation by d of z. And the reason why I'm doing this is because if I take this over here and flip the sign, I'm going to say that this is Na plus d of z minus molar flux of A, and then divide this by d of z. This is actually a first derivative, so I can just simplify this to d of molar flux in regards to the change of the z direction. And I'm just going to go ahead and flip signs for everything else. This is negative, and we divide by d of z across all terms. And we get something like negative r of A plus d of molar flux of A over d of z equals negative change of concentration of A over some change of temperature. And now what we're going to have is the final equation, which is change of concentration of A over change of temperature plus the change of molar flux in the z direction minus the rate of formation equals 0. And this is the final equation that we were looking for. So again, just to kind of walk back to what the question was asking, it was asking us to derive an equation of continuity for component A diffusing in a unidirectional system. So we took the molar flux of A, the concentration of A, and this rate of formation that we said was per volume basis, and simplified all terms to get this really neat equation over here, which shows the change of concentration in regards to temperature and how it's impacted by the change of molar flux in regards to some direction, which we said was d z in this case, and the rate of formation, which subtracts from the total equation, how all of this results in a equation that equals 0 in this case. So let's go ahead. I'm going to go ahead and duplicate the page just so I can get the questions really quick, and then I'm going to erase. This is just so I can have my questions still up here. Think of this as like wiping down the whiteboard. So now we're asking to explain an equimolar counterdiffusion, or how a equimolar counterfusion arises at a vapor-liquid interface when the enthalpy of vaporization is independent of composition. So this is a this is an interesting problem. So first rule I'm going to make for myself is that I'm going to assume that we're in steady state. I'm going to say that Na of vapor plus Na of liquid, or I should just say, our molar liquid, our molar flux of liquid, or molar flux of vapor equals 0, right? So what I can say is that the molar flux of vapor in this case equals the negative molar flux of A or liquid, right? And so the enthalpy of vaporization, if I were to apply it in this case, so let's say Na of vapor, enthalpy of vaporization equals the negative molar flux of the liquid, change of heat of vaporization. If we look at the equation in this case, you can kind of see that it doesn't really matter if we have this uh change of heat of vaporization for this system if it is independent of composition, because in this case, because we assume that we're in steady state, the molar fluxes are equivalent to each other, and if we're in the same composition, our heat change of enthalpies of vaporization are also the same in this case. So what I can do is just cross these out, and we can see that the system is actually independent of that in this case, and that our molar flux of vapor, not viper, vapor equals our negative molar flux of a liquid. So let's now look at a catalytic surface in this case, right? So we're trying to look at the total molar flux of N related to Na when we have a catalytic surface with the following reaction of A turns into 2B and 3A turns into B. So let's go ahead and do that. I'm going to draw a simple equation over here, which is A over some catalytic surface, which could be anything in this case. And then we have, it just turns into 2B. So the algebra for this isn't like, okay, it's easy, but it doesn't, at least in my brain, it wasn't exactly like the most straightforward thing, but it's really easy. You just don't get caught up in the wrong thought process with it. So if we want to look at the total molar flux, right? So we have N here, our total molar flux of the system. We know that this equals the molar flux of component A plus the molar flux of B. Now I'm going to do the same thing where I'm going to make a steady state system really quick. Where in this case, this would be 2Na equals, I mean, plus molar flux of B equals 0. So if I simplify this, I get the molar flux of B equals negative 2 molar flux of A. And now when I sub this in, I get N equals negative molar flux of A. So what does that actually mean in this case? If when I say I have a negative molar flux of A, what that means is that my molar flux is in the direction of product. I am creating more product than I am consuming reactant in this case, is what this is saying. So now let's go ahead and look at a case where we have something like 3A turning into 1B, right? If I have something like this, the algebra is again kind of straightforward. We have 1 over 3 molar flux of A plus molar flux of B, which then means that molar flux, goodness, molar flux of B equals this would be negative 1 over 3 Na, which if we go ahead and simplify this, this would be Na minus 1 over 3 Na, which then means that our total molar flux equals 2 over 3 molar flux of A. So what this means in this case is that we're consuming more product than we are I mean, we're consuming more reactant than we are producing product in this case. So that's for a catalytic surface in this case, that's kind of the quick algebra that you can do to kind of quickly determine the relationship between reactant and product.